Okay, in this video, I'm going to be using a differential energy balance to derive the heat diffusion equation for cylindrical coordinates. So here we have the cylinder, and we're looking at the heat flow through the cylinder. So from the top through the bottom. And we can say that this is in the z direction. And then if we want to look at an axis, this is going to be the radius, or rather the change in the radius, and we're going to also look at the change in theta, or the angle here. And so it's going to be like a shaded region, and this z-axis is what's going through the surface. That's kind of the axis that we're looking at for this situation. And then this is going to be similar to in the last video, a similar equation where we multiply it by the volume, but this time it's going to be the change in theta times the change in the radius times the change in the distance of r, and that's from here to here, and that's this distance. But because theta and r are both in polar coordinates, we want them to be in Cartesian coordinates, so we have to multiply this by the radius to get this in the right coordinate system. And then, similar to the last video, we first need to know what the stored energy is. So the energy stored is going to be equal to the density times the heat capacity times the change in temperature over the change in time, and then times the volume, which we just said was the radius times the change in theta times the change in the radius times the change in position or length. And then we need energy generated also. This is energy generated, and that's going to be equal to the change in heat flux, and then again times the volume, which was the radius, times the change in theta times the change in the radius times the change in position. And then remember that the net heat flow is equal to the heat flow in minus the heat flow out. So the heat flow going in is just QZ, which is just the initial heat flow, and then going out, it's going to be the initial heat flow plus the change in heat flow over the change in position times the change in position. So then that's going to leave, if we plug it back into this equation, we are going to have net heat flow is equal to initial heat flow minus initial heat flow plus the change in heat flow over the change in position times the change in position. And then this will just simplify to the change in heat flow over the change in position times the change in position. And then, like I was saying earlier, this is showing this change in position here along the x-axis. So now we want to do this again, but we want to model the change along the radius. So this was in the z direction. So then the net heat flow in the r direction, it was going to be the same thing, but instead of dz and qz, it's all going to be r. for the change along the radius. So I'll just do blue. And this will be the change in heat flow on the radius over the change in the radius times dr. And then theta is also changing. So that's this arc and this arc. So again, I'll make it orange. So the net heat flow is equal to the change in heat flow theta over d theta times the change in theta. And then these, we can relate all of this together because we know that the energy stored is going to be equal to the energy generated plus the net heat flow of all of these. So I'll just do Z plus R plus theta. And that's these three net heat flow equations. And then just like in the last video, we can apply Fourier's law here to all three of these equations. So remember that Fourier's law is the heat flux is equal to the negative thermal conductivity times the area times the change in temperature over the change in position. So this Q, we can plug that in here for all of these equations. So in the Z direction, that's going to look like d over dz times the negative thermal conductivity times the area for this one is going to be the radius times d theta times dr, and then we're going to still multiply it by dz. And then we have in the r direction, this will simplify to d over dr times the negative thermal conductivity, and then the area in this direction is still the radius, but it's going to be multiplied by d theta times dz, and then this whole thing still multiplied by dr. And then for theta, it's going to be d over d theta times the negative thermal conductivity times the area is the radius times dz dr, and then multiplied by d theta. And I explained this in the last video that we want all of these volumes, well, in the last video, all the volumes canceled. So you can see that here, that this, and then all of these are now having the same volume term there as well. And then I forgot up here that these should all still be negatives because you have to distribute the negative sign there. So over here, this would all be a negative as well. So when I plug all of these up here, the negative k values won't be negative anymore because those will all cancel out. So now before I plug these in, I have to fix a few of my mistakes. So here, this net heat flow, I need to get it out of polar coordinates. So this d theta term down here, we have to multiply it by r. So then this makes this 1 over r in this equation. And also I forgot this dt, or the change in temperature over the change in position. So then we have to multiply that, or we have to plug those in rather to the heat flow equations here. This is the change in temperature over change in position in the z direction, change in temperature over change in position in the r direction, and change in temperature over the change in theta. So now let's plug all these in. So using this equation here, the energy stored is density times heat capacity times change in temperature over change in time times the volume, which is R dr d theta dz. And that is equal to the energy generated, which is the rate of heat flow times the radius times volume, and then plus all of these heat flow equations. That's in the z direction. This is going to be in the r direction. So this is the thermal conductivity times the radius times the volume times the change in temperature over change in position in the r direction plus d over d theta times the thermal conductivity times 1 over r, and then times the volume, and then this is the change in temperature over the change in theta. So now looking at this, we have all of these volume terms here. These will all cancel. So we can simplify this again. Density times heat capacity, change in temperature over change in time, times the radius. It's equal to the rate of heat flow times the radius, plus d over dz of thermal conductivity times the radius, the change in temperature over change in position on the z-axis, plus d over dr, thermal conductivity times the radius times the change in temperature over change in the radius, plus d over d theta times the thermal conductivity, 1 over r, I guess that's fine, change in temperature over the change in theta. So I'm going to simplify this a little bit, or I guess clean it up. So this side will stay the same. This term can stay the same, but I can simplify this here is just the second derivative, the change in temperature over the change in position. I'm also going to factor out the k's here. Like that. Plus, this is plus 1 over r, because we're dividing the r over, and then d over dr. Like I said, this was differentiable, so this stays the same. Plus 1 over, this is now r squared, times the second derivative of the change in temperature over the change in theta. So this is the final heat diffusion equation for cylindrical coordinates. And now if we use the same equation that we just derived, but this time we're looking at a case of steady state with no heat generation and heat flow is only in the radial direction. That means at steady state, this is 0. No heat generation, generation is 0. And we are only looking at the radial direction. So that's this right here. So we can rewrite this. That's 1 over r, d over dr, r dt over dr, all this is equal to 0. And then the alpha term is still here as well. But then because this is equal to 0, when we multiply this over, same with the r, those are going to be 0 as well. So we're left with this equation that d over dr, r dt over dr is equal to 0. And now we can integrate this. So we take the integral of both sides, and we're left with r dt, or the change in temperature over the change in r, is, plus c is equal to 0. And then we want to get this on the same side. So we have dt over dr is equal to c over r. And we multiply this over dt, the change in temperature is equal to some constant over the radius times dr. And then we integrate both sides of this as well. And this is going to be evaluated from T1 to T2 and R1 to R2. So this is going to give us that the change in temperature is equal to the constant times the natural log of R2 over R1. And then to solve for C, we can say that C is equal to delta T over, or rather the change in temperature over the natural log of R1 over R2. And we plug that back in to this equation. Change in temperature is equal to change in temperature over the natural log of R1 over R2 times the natural log of R2 over R1. Here's that equation. And now we want to do another analogy to the voltage equation again. So now with this, if we look back at this equation, we're trying to find the thermal resistance here. So we can do what we did in the last homework video where we related to Ohm's law, which was the change in voltage is equal to the current times the resistance. So to relate these two ideas, relating Ohm's law to find the thermal resistance, we need Fourier's law again. So again, this is the heat flux is equal to the negative thermal conductivity times the cross-sectional area times the change in temperature over change in position. And then because we're talking about the cylinder, this change in position can be dr, and the area, it's going to be the cross-sectional area of the cylinder. So we can just say that the height is going to be 1 to make things simpler. So we can have this equation that the heat flux is equal to the negative thermal conductivity times the cross-sectional area, you can say is 2 pi r. And then dt over dr is here. We already found that. It's right here. And then we know what c is. So we can write that in as well. If I move it over. So this is going to be times 1 over r times c, which we said was change in temperature over the natural log of R1 over R2. And then while we're here, I'll just rewrite this to be T2 minus T1. And then looking here, the R's will cancel, and remember in the last homework, I talked about this as well. But I'll do different colors. This is the change in temperature, which is similar to the change in voltage here. And looking at the current is flowing through the circuit, and this is the heat flow. So we can relate those two together as well. So then we can simplify this and say that the rest of this equation here is going to be the thermal resistance. So let's rewrite all of that as well. And then, well, first I wrote this wrong. Okay, and now when we rewrite this, it's going to be delta T, or the change in temperature, is equal to the heat flux times, it's going to be natural log R2 over R1 divided by the negative thermal conductivity times the area, which is 2 pi. And then, like I said before, because it's a cylinder, we have to multiply it by the height as well. So we can put the h there for the height. So this is final equation relating the heat flow to Ohm's law, and we can say that this term here specifically is the thermal resistance.